All right, this is Unit 2.6 on rational functions. So what is a rational function? A rational function is takes the form of, we're going to call it n of x divided by d of x, just the numerator and the denominator, where both the numerator and the denominator are polynomials, and the denominator has a degree of at least 1, or 1 or more. Basically, the new thing with rational functions is that we are dividing by a polynomial that contains a variable. So where that makes things complicated and something we always have to be aware of, something we always need to be aware of with rational functions are values that make our denominator equal 0. We know that we can never divide by 0, so that'll be a constant kind of back of your mind concern throughout this section. The simplest rational function you can see here is graphed is 1 over x, and with the stipulation that x must not equal 0. You can see here our graph in your notes, and what we notice here is that our domain is that it's all values except when x equals 0. So in interval notation, we would write this from negative infinity to 0 in union with 0 to infinity. As far as range goes, we can see from our graph that we won't ever touch the x-axis. So again, our range will be very similar in interval notation. We'll go from negative infinity to 0 in union with 0 to infinity. All right, so we'll save that domain and range complications in a little bit. The other way we can describe these functions is using something called arrow notation. You may remember this as how we described end behavior of polynomial functions. And for this particular function, we would say that as x goes to infinity, as we go to the right side of our graph, f of x goes to 0. Right, as we go to the further and further, we are dividing by a larger and larger number, so the result gets smaller and smaller. And similarly, as x goes to negative infinity, again, f of x goes to 0. We can also describe asymptotes, vertical asymptotes, which we'll talk more about in a minute. As x approaches that vertical asymptote at 0 from the left, you can see that minus sign, that we would describe that as from the left. F of x goes to negative infinity, and as we approach 0 from the right, f of x approaches infinity. So really we're describing the asymptotic behavior of this function. You may be asking yourself, what the heck's an asymptote? So that's where we go next. Vertical asymptotes come from values in the denominator that have not been divided out. It is a vertical line that that our graph will approach from the left to right, but will not touch. So in order to do this, we will find zeros of the denominator. Most often by factoring. These zeros, they're going to be x equals statements. These zeros will be our vertical asymptotes. So in the example here, we have x plus 3 divided by x squared minus 9. Well, if I factor my denominator, I'm going to get x plus 3 times x minus 3, and you can see that these x plus 3's could cancel. Our graph will resemble 1 over x minus 3. This is our simplified form, and this is where we can find our vertical asymptotes. We will have a vertical asymptote at x equals 3. The canceled 0, which we see at negative 3, this would create a hole in our graph. We would have a hole or a jump discontinuity where x equals negative 3. We can actually evaluate the specific coordinates where that hole exists. If we were to plug in negative 3 to the simplified form of the function, we would say that the hole occurs at 1 over negative 3 minus 3, or 1 over negative 6. So the coordinates of this jump discontinuity, or this hole, would actually be negative 3, negative 1/6. So vertical asymptotes come from the denominator. They come from simplified form, and they are the non-canceled zeros of the denominator. Horizontal asymptotes are a little bit different, and they do behave differently. I think it's worthwhile to treat these fundamentally differently than vertical asymptotes. We can cross horizontal asymptotes occasionally. Horizontal asymptotes really describe the end behavior of a rational function. And if I want to identify those horizontal asymptotes, I need to look at the degree of the numerator and denominator. Really, what we're looking at is how do these degrees compare? Well, there's three situations. First, when the degree of the numerator is less than the degree of the denominator. In this case, we'll have a horizontal asymptote at y equals 0. If the degrees are equal, the ratio of the lead coefficients is the horizontal asymptote. So it will be the lead coefficient of the numerator divided by the lead coefficient of the denominator. That will represent our horizontal asymptote when the degrees are equal. And when the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. So we're going to look at a few examples together here to just identify asymptotes and see if we can make sense of it. So here on page 2 of our notes, we have an example, f of x equals 1 over x. Well, I can never divide by 0, so the restriction in my domain, right, the point of discontinuity is going to occur at 0. All right, we saw this already. Everywhere else, this function would be defined. In this particular case, the degree of the numerator is 0 and the degree of the denominator is 1, so the degree is larger on the bottom. So we will have a vertical asymptote at the line y equals 0. Oh, I'm sorry. I have that. That's our horizontal asymptote at y equals 0. Our vertical asymptote will occur at x equals 0. That's because we can never divide by 0. So the quantity in our denominator that would get us to that would be 0. So that's where we are going to have a vertical asymptote. In example 2, we have 2x squared divided by x squared minus 1. I think it's worthwhile, if you're able to factor either the numerator or denominator. It's a little bit easier to see our vertical asymptotes and other restrictions. Our domain here, well, I can't have a 0 in the denominator, and that would occur at 2 places. That would occur at -1 and +1. Oh, sorry, miswrote. So we would write our domain with 3 intervals from -infinity to -1, -1 to 1, and then 1 to infinity. Those discontinuities are vertical asymptotes. There's one at x equals -1 and another at x equals +1. In this case, the degree of both the numerator and denominator are the same, so we would divide their coefficients. Our horizontal asymptote would equal y equals 2 over 1, or just y equals 2. Our third example here, we have x squared plus x minus 2 over x squared minus x minus 6. And again, factoring is our friend. It allows us to simplify our fractions where possible. So my numerator is factorable to x plus 2 times x minus 1. And my denominator, x, let's see here, minus 3 times x plus 2. Well, I can see that x plus 2 is a shared factor in the numerator and denominator. Even though we canceled that quantity, we still need to account for it in our domain. So when I write my domain here, it goes from -infinity to -2, and then -2 to +3, and then finally 3 to infinity. Again, I just want to repeat that. Even though we canceled this particular factor, if we were to plug in -2 to our original denominator would be 0. Therefore, we must account for that canceled discontinuity, even though it doesn't appear in the simplified form, right? Our simplified form of x minus 1 over x minus 3. We only have one vertical asymptote here. It's going to occur at x equals 3. As you can see in your notes here, this is found for the simplified function, which we have at the top of our screen. We have a point of discontinuity at negative 3. In order to find the y coordinate of that discontinuity, I can plug in that negative 3 to my simplified form. In this case, I will have negative 4 over negative 6, which will simplify to positive 2/3. The relationship between the degrees of the numerator and denominator is that the numerator degree equals the degree of the denominator. So our horizontal asymptote will be 1 over 1, which we would simplify obviously down to 1. I'm going to chop this video into a second part. We're going to talk about graphing rational functions next. I'll check in with you guys on those graphs in our next video.